Hello everyone, my name is Gustavo Paneiro. I'm an assistant professor at Tecnico Lisboa from the University of Lisbon and researcher at Serena, Center for Natural Resources and the Environment. If you have any question, please send me an email to gustavo.paneiro@tecnico.lisboa.pt or follow me at Twitter or LinkedIn. Well, the title of my presentation is Artificial Neural Networks for Ground Vibration Modeling Produced in Rock Excavation. And so I'm going to show you some works that we've been done, and they are published, and I will give you also the references of those published works. So let's go further. So this is an outline of my presentation. I will start to talk about the environmental aspects of blast-induced ground vibrations, and then I will talk a little bit of blast-induced ground vibrations propagation modeling, and then the application of artificial neural networks for blast-induced ground vibration modeling using two approaches, which corresponds to two different published works, the cross-validation approach and a bi-level optimization procedure. Both of them are, we developed these two, or we applied one and developed the second, these two approaches, because we were very concerned about the overfitting issues. And at the end, I will present some conclusions. So, considering some environmental aspects of blast-induced ground vibrations, well, we all know that if we find a rock mass, it is very expensive to use mechanical ways to perform the excavation. So blast offers higher technical and economic advantages to proceed to the excavation works. Nevertheless, the production of blast-induced ground vibrations can lead to serious environmental impacts. Those can be related to dust, to noise, to fly rock, or of course the ground vibrations. And actually, I present you there some very well-known excavability advocates from Franklin in 1971, where, considering the axial compressive strength of the ground, the discontinuity spacing, or the point load strength index, we can find the suitable way to perform to the excavation. Also, there are, during the next, well, let's say 1 decade, the environmental restrictions performed by standards and legislation become higher and higher. For example, I present there some standards for ground vibration control, considering, well, two types, let's say in this way, two types of standards: the structural damage standards, and in Portugal we have the Portuguese standard NP 2074 that was revised in 2015, and in Europe I present you 3 examples. One, the DIN 4150 from Germany. From the UK, we have the BS 7385, and from Switzerland, SN 640312. Concerning to human disturbance, which is even more restrictive than the structural damage, of course, we have the ISO 2631. And so these standards imposed lower allowable blast-induced ground vibration amplitudes, and of course, as I told you, the standards for human discomfort or human disturbance are even present even lower allowable blast-induced ground vibration amplitudes. And so, considering this, we have to understand a little bit about the propagation of blast-induced ground vibration. So we use explosives, and we detonate explosives in a very controlled way to crush the rock. And there is, that I present you in the upper graphical representation, I present you the mechanics of rock fragmentation from blasts. And this mechanics considers a dynamic stage and a quasi-static stage. Well, the dynamic stages are related with the propagation of very high amplitude or very high stresses, radial and tangential stresses, and the quasi-static stage is usually concerned with the formation of volumes of gases that are from the result of the chemical reaction of the explosives. And so, depending on the amount of released energy for a certain distance, elastic waves continue to propagate through the ground. And so, in the lower figure, you can find a schematic representation of the different zones that we can find from the blast, from the blast hole, and with the higher distance. So we have the blast hole filled with explosives in the center part here. I cannot show you, but we have the blast hole filled with explosive at the middle. And then we have a transition zone. In the transition zone, we can divide it in 4 parts. The hydrodynamic zone, where the rock behaves like a fluid, almost like a fluid, a plastic zone, a fragmented zone, and a fractured zone. In a higher distance, we have the seismic or elastic zone, where the stress wave, the waves that are produced from the blast behave like elastic waves or seismic waves. Well, given this, either the stress waves are elastic waves, so the ground behaves elastically, so we can have some not so good effects about the blast-induced ground vibrations. So it can affect the normal work of sensible equipment or instruments. This is the least severity effect. Then the second one, which is more severe, population disturbance that leads to complaints. And the most severe effect is the structural damage, particularly in heritage buildings. We modeled the blast-induced ground vibrations. Well, we modeled the blast-induced ground vibrations considering the blast, the source, the ground, which is the propagation medium, and the buildings, the type of building, which are the targets, actually. And several works were performed during the years, and I present you here some examples of 23 models, mathematical models to model the blast-induced ground vibrations. This summary was presented by Kumar et al. In 2016, and usually traditional models considers only one predictor. The predictor usually is distance, okay, or a relation between distance and the amount of explosive, usually the maximum amount of explosive per delay. And they usually are linear-based models. They are linear in the parameters, but not in the predictors. The problem here is in these models is that there are some generalization issues that arise here. Well, we can use very well these models in one place, in one project, but we cannot use the models in other projects. To overcome these generalization issues and to get better predictions, some authors developed some works that considers geological and geotechnical or geotechnical parameters as predictors And we have there 4 examples. One in 2008, 2011, 2015, and 2016. What concerns to the work of Kumar et al. In 2016, as you can see there are the model considers FC, which represents the axial compressive strength, and there are several ways to consider the axial compressive strength, and the distance also, and also the unit weight. Okay, in this work, Kumar et al. Could make a pretty good prediction from the amplitudes of the blast-induced ground vibrations at certain targets. In what concerns to the application of artificial neural networks for blast-induced ground vibration amplitudes using the cross-validation approach, this was a work developed by me and one of my master students in 2021, and the study considered a bibliographic database with 1,114 entries from 21 open-pit blast sites and 12 different geological contexts. This bibliographic database was published by Nichols et al. In 1971. The model, in the ANN model, we considered 16 inputs with 4 quantitative predictors: the blast hole diameter, the blast hole length, the maximum amount of explosive per delay, and the distance, and 12 dummy variables from the geology qualitative predictor. So since we have 12 different geological contexts, we had 12 dummy variables from the geology qualitative predictor. And so before we start to assemble the ANN architecture, we had to select from a set of different parameters, blast design parameters, geometrical parameters, as well as quantitative of explosive parameter. And we performed a Pearson and Spearman correlation matrix to avoid the use of statistically correlated predictors. And we saw some dependencies between the blast design parameters, which are marked at yellow in that table, and some dependencies with the blast hole length, which are marked with in green in that table, in that matrix, Pearson and Spearman matrix. And in the end of the day, we found the 4 quantitative predictors, which are the ones that are concerned, that are related positively or negatively with the ground vibration amplitudes that were registered. After that, we developed several artificial neural network architectures. But some of the architecture parameters were considered to be constant. For example, the number of hidden layers, we only considered 1 hidden layer. The number of neurons in the layer, we considered 1 to the maximum of 15. Okay, with why the maximum number of 15? Because it was the number of input variables. Different activation functions, ReLU, hyperbolical tangent, and sigmoid. 4 different optimizers, and we increased the number of epochs. As you can see there, we could develop 45 different architectures. We developed all these, the ANN models in Python using Pandas, Matplotlib, scikit-learn, and Keras libraries. The default cross validation, which were presented for the first time by Pickard and Cook in 1984, well, we we used this approach as a way to virtually increase the data set. And so how this works, we divide the data set in four equally parts. Okay, so 25 for the first set, 25% for the second set, 25% for the third set, and 25% for the fourth set. And for each ANN, 75% of the data was used for training, which are marked in each case in yellow, and 25% highlighted in blue were used for testing. And the procedure was executed for 4 times with the 4 different combinations. So we increased, let's say, like that, the training at 4 times the data set dimension. Considering the best fit models for in the different hidden layers dimension, we got the hidden layers dimension DCE from 1 to 15, the different optimizers. The best models considers as the best optimizers the RMS Prop and SGD, and the activation in what concerns to the activation functions we have, well, basically the tangent, hyperbolic tangent, and sigmoid functions, and the number of epochs were at minimum 400 epochs. And as you can see, we have a mean absolute error mean and mean absolute error minimum. The R squared mean and the R squared max for each model or for each architecture. And as you can see, the best fit model was the one that offers the lowest MAE mean and the lowest variation or standard deviation from the R squared. And considering these 2 parameters as the cost parameters, we can check out that there is no overfitting by this model with 12 neurons in the hidden layer. Here I present the evolution of the MSE, the mean squared error, during the train and during the test for the different epochs for the best fit model, and the predicted versus observed vibration amplitudes, and in the right graphic. In this right-hand plot, we can see that, well, that we got very good predictions, and actually the errors are more or less homogeneous throughout the increase of vibration amplitudes. In what concerns to the bi-level optimization, this work was performed in 2020. We considered a database with 1,188 entries from 206 blasts and 12 monitoring points. And this was the source of the vibrations were blasts from the underground rock excavation. Let me say that for the cross-validation approach, we the excavation was in open pits. And so, and in this work also, besides the underground rock excavation, this work was performed in the urban environment where the restrictions are much more evident. Also, the RMR, rock mass rating, was used as a quantitative predictor for the geotechnical characterization. The other predictors that were used were at the same way quantitative, the maximum explosive amount per delay and the distance, besides the RMR as quantitative predictors, and qualitative predictors, the building type. And as you can see, the rock was granite with coarse to medium grain basic granite from Oporto's area, which is in the north of Portugal, and the lower image you can find several monitoring points that were considered in the study for the monitoring. So for this, we use the MATLAB, a script in MATLAB, and the bi-level optimization considers two levels, as the name says. An upper level where we want to minimize the archaic information criteria, and a lower level where we minimize the sum squared error. We have here a global optimizer, gamma, which is usually heuristically obtained. Why? Because usually in the initialization of the neural networks, we have a random attribution of weights. And so we start from the lower level by applying a multi-start procedure, and from that multi-start, we want to get the
Professor Yan? Hello? I think we lost Professor Yan. Hello, hang on.
I will call him.
Yeah.
I don't know what is the problem.
You can see that for more or less 100, no matter.
So now the voice is back. Not continuously.
Yeah.
Yeah.
The hidden length and age there, we can see that, well, from 100 starts, we got a minimization of the SSE, okay? This multi-start here is very important because of this random attribution of weights in the neural network initialization. In what concerns to the overall results of the bi-level optimization, we got the obtained results for this procedure, application of this procedure, considers a hidden layer size of 5 with the transfer function 10 sig transfer function, and we got an R squared of 0.962. We got this. We selected this one because it offers a smaller SSE and smaller AIC. These are the predicted versus observed amplitudes considered for both for all the data set on the left side plot, and on the right side plot only consider the test data. Okay, got pretty good results. Here we got the results from the estimated and observed amplitudes, considering the distance and the weight of explosive. And we also consider a analysis of residuals, considering here the studentized residuals, they follow a normal distributions that's desired, which we can find. We can conclude that the model is suitable for the database. Conclusions. So in what concerns to the cross-validation approach, the ANN with 12 neurons in the layer with the lowest MAE and standard deviation was considered. We got a greater generalization ability, and the MAC evolution in the training and testing and cross-validation suggests no overfitting. In the bio-level optimization procedure, in the lower level optimization, we got a multi-start procedure that minimizes the SSE because of the random, and we apply this because of the random ANN weight initialization. And on the upper level optimization, the minimization of ASC was used to improve the generalization and avoid the overfitting. The best fitted model considers 5 neurons in the hidden layer and a 10-sig transfer function. The residual analysis revealed that for higher amplitudes, the model offers good prediction results, and for lower PVSs or amplitudes, there is an intrinsic random variability. This approach offers a contribution for a more rigorous environmental control. These are the references that were used on this presentation. And thank you so much for your attention. Let me